Hi there. We are going to get started on some counting functions. So, just as a quick reminder, we're going to define a step here. One step is one line of code consisting of only primitive operations. And just to finish off this reminder, primitive operations include reading variables, basic arithmetic, it doesn't spell arithmetic, but whatever, setting variables or assigning them, or comparisons. All right, so armed with that information, you just move this over there, move this over there. We're going to combine this a little, put it over there, put it over there, so that we can move all this information up and out of our way while we work on this problem. All right, cool. So we're going to work through this problem. We're going to determine, oops, that's odd. We're going to determine, let's pretend like this is some kind of method f, and we have a precondition that we have some integer n coming in. So our question is, what is f of n in terms of the number of steps that it takes to finish f of n? So let's make our way through this exercise and figure out what exactly is going on here. All right, so we're going to start by looking at the fact that we have two for loops here. We have a for loop, or while loops, I should say. We have a while loop here, we have a while loop here. When we have nested loops, we want to make sure that we start by looking at our innermost loop first. So the first thing we're going to do is we're going to look at lines 5 to 7, and we're going to see what we can glean about those lines of code. So let's just do this in colors. We've got this right here. What can we tell about this part of the function? Pardon me. Well, we can see that from line 4, J starts off at 0. So this for loop here is going to start us off at 0. And then we can also see that by the time we reach line 5, line 5 tells us that we're going from J equals 0 to J less than K. And J counts up by ones all the way up to K. So the loop condition on line 5 evaluates to true for J equals 0, J equals 1, J equals 2, J equals 3, all the way up to J equals K minus 1 for all those values of J, right? On lines 5, 6, and 7 are all executed. So what does that actually mean for our function here? Well, it means that, this starts J off at 0, and we're going to go up to K minus 1. And remember, that's going to be inclusive there. And we have line 1, line 2, and line 3. There we go. Lines 5, 6, and 7 are all being run. And so once we actually evaluate this, what do we end up with? We're going to end up with 3K. Now, if we're going to actually show why that's the case, we can take that J equals 0 to K minus 1 and put our 3 there. We're going to factor out our 3. We're going to end up like this. And then we can use that handy summation identity that we are becoming ever so familiar with, which is going to be B minus A plus 1. So here we have B minus A plus 1. What do we have going on here? 3K. There we go. I'll put the equal sign there instead of there. Okay. 3K minus 3 minus 0 plus 3. Of course, the 0 is nothing. The minus 3 and the plus 3 cancel each other out, and we're left with that 3K. So we can see that this is 3K. Now, the one thing that we don't want to forget is that, of course, we have another 1 here. And we have another 1. This 1 is representative of the time where J is greater than or equal to K, and line 5 evaluates to false. We don't want to forget about that time. So I'm going to add that right up here, 3k plus 1, leave that all together for right now, just so that we don't forget it, right? So the loop condition in line 5 does get tested for one step. It evaluates for false, and then we skip down to line 8. So that total line 5 to 7 ends up costing us 3k plus 1 steps. All right, so we have that sorted out. So now let's consider the next loop here. So the next loop we have to consider takes us from here, sorry, 3k plus 1, and it goes and it cuts all this in here. Okay, so what can we see from here? Well, we can see that this is a 1 and this is a 1, right? We can see that we have that 3k plus 1 in the middle. So from line 1, we know that we're starting k at 0, and line 3, when line 3 is reached for that first time, we know that k is 0, and from line 8, we know that k is counting up by 1 each time. So thank goodness, this is relatively straightforward as well. So what are we going to do? I'm just going to give myself some space here. I'm in pink. So when we look at that loop condition on line 3, we want to ask ourselves, when does it evaluate to true? Well, it will evaluate to true when k is 0 and 1 and 2 and 3 and 4, all the way up to n minus 1 again. So for each such value of k, the code will execute lines 3 to 7 to 8. It will execute all of them. It executes lines 3 all the way up to 8. So as long as this is true, it executes here to here. That includes this whole business here, and then it comes back up to the top and does that check again, right? So we have to remind ourselves of that extra plus 1 in there. So what do we have? We're going to have the number of steps for one iteration is we're going to do this check here. So that's 1 step. We have this check here, which is 1 step right here. And we have this check here, which is 1 step. And we have this that happens in 1 iteration as well. So let's just write that down. 1 iteration is 1 plus 1 plus 3k plus 1 plus 1. What does that end up equaling? 3k plus 4. Fantastic. So now that we've got that, that's how much 1 iteration is, but we need to determine what it's going to be in total once we do all the iterations. So we know that k will start us out at 0, and we do know that it's going to go up to, but not including n, so up to n minus 1, and it's going to run for this whole term here, 3k plus 4. Now, it's much easier to separate out this term into 2 terms, so that's exactly what we are going to do. We are going to go ahead and say k is equal to 0 to n minus 1, 3k, plus that same sigma, that same summation with a 4 there. And I will also here factor out that 3 because I want this to start to look a little bit more like our, what are they called? Our identities. Lost the word identity there. Some days are trickier than others for words. All right, so we can do this. We factored that out. Fantastic. So now that we have gone ahead and factored that out, we're going to go ahead and apply some of those identities. So I didn't actually grab those identities. Let's go grab them. We can just grab them from our note set. We can grab, I think we can grab this one, copy. And we are working our way through this one here. There we go. So given those identities, we can sort of see what's going on here. Now, one is going to go from j equals 1 to n, and then the other one is going to go from j equals a to b, and it goes over 1. So what exactly is happening here? Well, so this can now be evaluated, and what we're going to end up evaluating this to ends up looking a little something like this. It gets 3, I don't know why I keep switching it there. 3n minus 1 over 2 plus 4n. Now, let's just break down why this here is actually the case. So let's just start by breaking down, let me switch colors here, this one, because that'll be the easier one to understand first. This one uses that first identity where this is like the B, this is like the A. And so we say 4 times n minus 1 minus 0 plus 1 Those cancel out. That's just 0. We get 4n. So that one's not too bad to understand. That one, hopefully, we can look at and feel pretty good about. But now this one is a little bit trickier to follow why this is the case. So let's really break down what the heck is going on here. Pardon me. So the common summation identity that we know is as follows. We know this one, right? It's right here. This is the one I'm just rewriting it with the value k in there for a second. But it doesn't matter. We know that this is the common summation identity and we're familiar with it. And it starts at k equals 1 and it goes to n. However, it is of course possible and in lots of contexts as computer scientists that we see different bounds. In fact, in our current example, the bounds that we're talking about are, let me grab them right here, k equals 0 to n minus 1. So they are a little bit different. So we do need to reindex that summation. So let's think about what this actually means for a second. When we do this, k equals 0 to n minus 1, we're basically saying 0 plus 1 plus, oops, I should probably put some pluses in there instead of commas, plus 1, plus 2, plus 3, etc., all the way up to n minus 1. That's what we're actually saying. So to relate this summation to the identity above, we're going to need to reindex it by shifting some bounds around. So first, we're going to reindex our variable. So let's just for a second define a new variable m. Let's define m to be equal to k plus 1. So then when k was 0, m would have been 1. And when k is n minus 1, m would have just been n. So now we can rewrite our summation with our new variable. So let's go ahead and do that right over here. We would end up with k 0 to the n minus 1 over k is going to be the same here as now saying m equals 1 to n m minus 1. So we also have to adjust for it right inside here, right? We can't forget to do that one as well, because what does k equal? Well, just as a reminder, you look right back here, you'd have to move this 1 over to this side, and k would be equal to m minus 1. So that's how we get that number over there. So now when we simplify this expression, what we can actually do is separate it out just like we were doing previously. So now we're going to have m equals 1 to n over m plus m equals 1 to n. Oh, sorry, not plus. I guess we can take out the minus 1 to make our lives easier. There we go. We can do it like that. So now when we break this down, we can actually see that m equaling 1 to n is the familiar sum of the first n integers. So let's take this first term over here and turn it into the sum of the first n integers, just like this, as we'd expect. And then m equals 1 to n is just us adding 1 for each of those integers. So of course it will just sum up to n. So this ends up being minus n. Now, when we go back to our original 0 to n minus 1 scenario, we can now use this information and plug it in. So we can say that k equals 0, n minus 1, all the way up to k is going to basically be the same as saying n plus 1 over 2 minus n. And now if we're just going to take one n out, just notice what I'm doing here. This is a plus, this is a minus. If we do the algebra here, this is equivalent to saying n minus 1 over 2. And so what this means is we've taken our original identity and we've just sort of zhuzhed it around a little bit. So if we come back up to here, we're basically like adding one more identity to our pile here to help us understand what's going on. We're going to add one more identity here. Oh, that's going to be in the way, thanks to the line of there. We're going to add one more identity right here, where we can say j is equal to whatever we just wrote. 0 to n minus 1, n minus 1, and then this will be over j. And instead of n times n plus 1, we end up with n times n minus 1. So there we go. We have done our reindexing, and we now realize that this is an equivalent statement. And thanks to that, we're going to see how we then plug that in right here. Because now I'm using my new identity that I just sort of described below to do this right here. So we have our 3, and then this identity right here, where it goes from k equals 0 to n minus 1, uses this. So n times n minus 1 over 2. And that's how I'm going to get that value. I'm going to get 3n times n minus 1 over 2 plus 4n. And then at this point in time, we also want to make sure that we don't forget. I'm just going to pick this up here for a moment as I move down. This was like all, actually, you know what? This was all the aside that helped us determine what that last identity is. So I'm just going to scoop it up. I'm going to move it over here, and I'm going to highlight this identity like this, because that is the identity that we just got to using all that orange text over there. So we'll just do that. That's how we managed to figure out what our term needed to be. So now I can continue with my proof over here, and I can say, don't forget that line 3 evaluates to false to stop the loop. Therefore, our function now looks something like this. We're not done yet, but this is where we're at so far. So that whole business right there, we're really close, aligns very beautifully with the n value over here. There we go. With all that pink. Let's go ahead and do this. Here. Okay, so that's all the pink. I wish that I had done this in purple so that we could be somewhat consistent here. Okay. All right, the last thing we have to do that we haven't touched on yet is right up here. We have to do that blue part, right? We have those two last lines of code that are not yet accounted for. And thank goodness they're each only one line each, which means that they are just a straight +2. Let's highlight that. Let's come down below and let's add that in. So lines 1 and 2 give us a +2. So we end up with an f of n being equal to those two lines plus the 3n n minus 1 over 2 plus 4n plus 1 that we got from the previous step. When we shove all of this together, we find that f of n is going to be equal to 3n n minus 1 over 2 plus 4n plus 3. So that has now combined all the different lines of code in order to create the number of steps, the total cost for this program. So this is the total cost of f of n. Hopefully this breakdown helps people understand how we ended up getting to this term. I know that this term right here was mighty confusing for some, so I'm hoping that this is going to be a better introduction to how this cost analysis ran. All right, thanks everybody, and have a great rest of your day.